Everyone, and welcome to anyone. Actually, I think looking around, I think everyone was here yesterday, but to those who weren't here yesterday, welcome to the convention. Usual sort of housekeeping, phones on the silent, please. If the phone rings, it's a complete round for everyone in the room at the bar at lunchtime. Fire escapes and all that stuff just over there. One of the things I remember from many years at the HF convention and now the RSGB convention is antenna lectures. And if you look, they seem to be in decline. And I think this is the only one on the agenda for the whole thing. And yet everyone will agree that antennas are something that, can be a mystery, you can't understand, and you'd always like them better. So what Mike is going to talk about, as it says there, is the 3 DXpeditions for the 6Gs group. And after this one, I'll be presenting our last DXpedition if you stay on for that after coffee, and how the antennas were decided. So, Mike Chamberlain, I'll say that again, Mike Chamberlain, G3WPH.
Thanks very much, Chris. And thank you for getting up early and coming and listening to a presentation.
We're all drunk.
The presentation is going to focus on the HF antennas, by which I mean 20 meters up to 10 meters. There's a couple of slides at the end on the LF part of the spectrum, but we did quite a lot of work on the HF end of the spectrum, and I thought I'd share with you the results we got from that. Happy to take questions at any time, especially from an audience of this size. I'll predict the first question, which is, why is it called the 6G group? And I learnt this morning it's actually a crowd-sourced name. It wasn't a name that was given to the team, that the team gave to itself. It was given by people feedbacking on forums, etc. And it's an evolving story because we started off. Well, let me just tell you about the DXpeditions first. The first one was to the Australs in March of 2014, TX6G, and that was at a classic South Pacific QTH. You can see on the beach, north-facing, antennas really easy to decide upon. You put a VDA in the water, point it north, open a can of beer, sit back and run DX for 2 weeks. The second DXpedition was Nui in September of 2015, and this presented a new set of problems because there's not a lot of natural beach on the island there. We ended up at a very nice QTH, but the problem was at the top of a 25-meter cliff, and there was really no access close to the beach itself. It was a case of we were going to be about 125 meters at least back from that cliff edge. And we'll see that really means you need to make a different decision for your antennas. The third DXpedition was to the Chatham Islands in October of last year. And again, a different sort of a location. We were we were on a promontory. The sea was never closer than 250 meters to the east and the west, and it was much further north and south. And we were about 70 meters above sea level. And there's another special characteristic of that QTH that I'll talk about in a minute. All of these DXpeditions were fly in, fly out, so no containers, no thought of Yagis and at the top of big towers. And we were very clear that UK and Europe was a priority for QSOs. You've got Japan to the northwest, you've got North America to the northeast. You're going to get plenty of QSOs in those areas with the regular sort of antennas, things that have got high angle radiation, but you're going to need some very good low angle radiation to get to Europe from any one of those deep Pacific QTHs. Now, I just knew this would happen. There we go. So, as I said first early on, it's easy in the South Pacific. You put up a VDA and point it north. I'm just going to talk about a VDA for 2 or 3 slides because it becomes the standard by which we can measure the performance of other antennas. So vertical dipole array, although some people will call the VDA a vertical dipole antenna, in the texts on the web it has both of those. Quite a simple concept. Quite a simple concept. A half-wave vertical radiator with a half-wave reflector behind it. Radiation's out towards that red door over there. There are really 3 classical feed methods I've seen for it. Well, there's one classical and a couple of oddballs, I'd say. The classic is just to put a 50 ohm coax feeder at this point, put a choke on it, current mode choke, and take the feeder back along the boom and then feed it out as far as you can, horizontally or sloping, probably not vertical because you don't want to upset the radiation pattern. Construction of these things is really simple because you can use a spider pole or fishing poles to form the vertical and the boom element. And Sainsbury's did very well in the sale of chopping boards because the crosspiece here was always made out of a Sainsbury's chopping board with some U-bolts on it. So why is it that the DXpeditions select this antenna? Well, first of all, a couple of examples of it. This is classic positioning on the seashore, close to the sea. The one mistake with that installation is somebody's run the feeder vertically from the... we'll get to grips with this in a minute. Somebody's run the feeder vertically from the back end of the boom, from the back end of the reflector down to the ground and across. Not a good idea. There's another one. This was an experimental unit that was built in a back garden. I tell you, it works far better pointing towards the sea than a swimming pool. So why is it that this antenna's got such a great reputation? This is an easy neck elevation plot of a 20-meter VDA with its base 0.1 of a wavelength above salt water. And you can see the answer to the question. That low angle lobe there is fantastic for DX. And before we talk a bit more about the characteristics of that, it's just worth looking at the arrival angle probabilities of signals on a DX path, say, and this path that was chosen for analysis here is the path between London and L7. As I said, Europe and UK was a priority. So when you start looking at the arrival angle of those signals, just look at 10 meters. No, just look at 10 meters there. Everything arrives at an elevation angle of below 1.9 degrees. 8 degrees. Thank you, sir. I'll get used to this in a minute. 83% of the radiation comes in below 5 degrees. And then, before I go back to the elevation plot we were using before, which was for a 20-meter VDA, just look at the 20 characteristics here. There's no radiation above 16 degrees. And 89% of the radiation comes in below 7 degrees. Now, 7 degrees is important. Try and remember that as we go back to the next slide. And the peak radiations are at elevations of 16 degrees and 17 degrees. I'm not sure I quite believe the 1 degree numbers there, but these figures come from HF terrain analysis program by N6BV, which comes free either with the ARRL antenna book or the ARRL handbook. David, you'll know which one it is. It comes with the antenna book. So if you want to go and play and look at these sort of characteristics.
Mike, are you able to actually verify this?
Sorry?
Are you able to verify it?
Absolutely.
Okay, tell me.
You just need to, no, you've got to wait for a few more slides. Who invited you? And another important characteristic here is that as frequency gets lower, as the wavelength increases, then you do get more and more more and more higher angle radiation coming in. And that becomes important when we look at why do some of the antennas that have got a slightly higher angle of elevation maximum, why do they work on the lower frequencies? Right, so I'll go back to the plot we had before. Now, the green line I've added there was the 16-degree line, above which there was no arrival on that path. So at one level, any radiation above that line is probably useless. It's not quite true, but it's a pretty good approximation. And if you remember, I gave you the figure at 7 degrees. Well, the peak radiation from this antenna, the maximum radiation, is in fact at 7 degrees. So that's right down there. So explains now why this antenna is so good for DXpeditioning. The gain figures up the top there, 10.7 dBi. Well, that sounds really impressive. What does it mean, though? We all know that the gain of a half-wave dipole is 2.14 dBi. But what does that mean? It's only 2.14 dBi in free space. And if you remember the classical donut shape of the radiation, then that is the maximum radiation in free space of that donut. Put that half-wave dipole above a piece of put it half a wavelength above a reasonably good Earth, and it's in fact got 7.2 dBi gain. And that often gets forgotten. And that 7.2 dBi gain will be at about 17 degrees. So that 10.77 looks really impressive until you realize it's only about 4.5 dBs higher than a dipole. The big advantage comes from the elevation angle here. The dipole will be up at 17 degrees. So that again explains why such a great antenna. So you put it on the water's edge. But what happens when the tide goes out? Because these antennas are very susceptible to height. So the red plot there was the original 0.1 of a wavelength above water. The blue plot, which I've added, is at half a wavelength above the water. Now, in the Pacific, in the deep Pacific, tides don't vary by that much. A couple of meters is probably all you're going to get. But it is probably more applicable if you're having to put it on a cliff, for example, which was our problem at the second DXpedition. And you see we've now moved to a much higher, the main lobe is at a much higher angle of elevation, fairly useless to us, in fact. Although there is it's still a useful lobe down here, but a lot of the power's gone where we don't want it. So as you go higher and higher in altitude, then the number of fingers in the lobe begins to increase, and more of the power moves into the high elevation angles. So that's what happens with respect to height when the water goes out. What happens when the tide's gone out and you've got a lot of sand, dry sand between you and the ocean's edge? So this trace has now moved to a VDA still at the same height, but over dry sandy soil. And you can see that the maximum radiation, the elevation has increased, and it's decreased somewhat in amplitude. So you've heard the stories, VDAs don't work if you build one in your back garden. They don't. You need to be on the ocean's edge. So, as I said, perfect solution for the TX6 DXpedition, but it wasn't going to solve the problem for Nui, where we were at the top of a cliff and back from that cliff edge. So we'd started looking at some alternative antennas, Yagi's, dipoles, and we analyzed each and every one of these. So I won't list them all out, but we did a fairly thorough investigation looking for an alternative. Some of them were going to be impractical from a logistics point of view. So how could we evaluate the performance of those antennas in a real-world situation? And there's a technique that we've built on and developed, is to take the output from the EasyNet analysis of the antenna and feed that into VOACAP, the Voice of America coverage analysis program. VOACAP seems to still be the gold standard for analyzing propagation possibilities. It's in the mode we used it, it does a point-to-point signal loss analysis, attenuation analysis, and from that can predict the performance. So for each and every one of those antennas, I created a three-dimensional plot. VOACAP gives you a plot like this, and it creates a file with the gain at 1 degree increments in azimuth and elevation around the sphere. And you can take that file and you can put it into VOACAP as your transmitting antenna and use that to analyze the path. Now, there's a lot of characteristics you put into VOACAP. It's not an easy program to use. So you need to put things in like the latitude and longitude of both stations. You need to put in the antenna gain models for both the transmit and receive side. It uses smooth sunspot numbers. And other parameters of interest are transmit power and the noise level at the receive site. In fact, you can model the performance of each and every antenna, which is what we did. And that results in some very nice looking plots like this. So this is for a single antenna. In the vertical axis, you've got frequency. And in the horizontal axis, you've got time. And this was actually on the Alofi to London path, which is the capital of Niue. So this was the analysis when the bands would produce some signals on that path. And it analyzes them in terms of signal-to-noise ratio. It actually uses the signal-to-noise ratio in a 1 dB bandwidth. And these colors here represent the signal-to-noise ratio on that path. So, for example, if I look at the 17 megahertz path here, oh, I need to say one other thing. As I said, it analyzes it in terms of a signal-to-noise in a 1 hertz bandwidth. That's pretty meaningless to most of us. You can equate that, a good CW operator will be able to, an average CW operator will be able to copy 24, a signal-to-noise ratio of 24 dB in a 1 hertz bandwidth. It's equivalent to 2 dB in a 200 hertz bandwidth. So most of you guys will copy that without difficulty. So that became the standard we began to use because these numbers otherwise look inflated and you think you've got S9 signals all the time. But so if we go back now to the 17 meter path, then anything with a signal-to-noise ratio of greater than 25 dB, which is the reds, the greens, the yellows, it's yellow when not projected from here, will produce a receivable signal. Back to 17 megs, and you can see that the band will open from about 8 o'clock. Oh, I'm going to do this the easy way. The band will open from about 8 o'clock UTC with signals. It will fall off again just after 2 o'clock, but then there'll be a second opening in the afternoon. So 17 megs able to analyze the signal-to-noise ratio at the receive station on that path. Sorry, the short path analysis. Now, very nice, colourful plot, but what do you do with it? How do you use that information to make a selection between the antennas? Now, as I said, we've got one of these plots now for each of the antennas we chose to use. So the answer to that is that you can extract the signal-to-noise ratio, say at 17 megahertz here, you can extract the signal-to-noise ratio at various points along the line there and plot those. So we did that, exported it into Excel, produced a plot, and you end up with something that looks very much like this. So this is a comparative signal-to-noise ratio now for each of those antenna, or for a number of antenna types. And these measurements were actually made at 21 megahertz. Not a great deal because we're doing comparative comparison between the antennas, and I could have well have done it at 20 meters or whatever. So now we've got signal-to-noise ratio measured on the basis there of 24 dB. 0 is 24 dB dB per hertz, and we've got the gains. So you look at the gain of the you've got time along this axis here. You look at the gain of each of these antennas, VDA in the ocean. Well, clear winner. Interesting, somewhat better than a 2-element Yagi at 0.5 landers above a dry sandy soil. VDA, the green one, VDA over dry sandy soil, shows us why we don't build one in our back garden. And because it's important later, an elevated ground plane with the base at 0.66 of a lander. 0.66 lander just happens to correspond with how high you can put it up a an 18-meter spider pole. So it looks a funny, but it does have some meaning. So obvious decision there, what you're going to go for.
You're not comparing apples with apples there, because your VDA is at the ocean edge, whereas your other antennas aren't.
That's a great introduction into the next slide. Thank you, John.
All right, how much are you paying?
Okay, so we now have these plots for each of the antenna types we wanted to look at. And it gets a little, you have to sort of apply a little bit of artistic license here. But I've done comparisons between the gains of each of those antennas and all of the antenna types that we had. And it produces this graph. So if you're ever going on a DXpedition, have a look at this graph, and it should, or this chart, and it should tell you what antenna to select. So, interestingly, I don't think many of you would have thought of this, or maybe I'm wrong, but vertically polarized 2-element quad, half a lander, i.e. on a cliff edge, over the sea, performs really, really well. And if you can put one of those up, you'll be good. 2-element Yagi, one lander above the ground, works extremely well. But look, right up the top there, VDA at the ocean edge. It's only 2 and a bit dBs down on the best performer. And you can work your way down through this table. It does have some interesting results in there. But the ones that I'm going to point out at the moment, because they're significant to the decisions we made, are the high inverted Vs. So if you've got a inverted V, you can get it to 1.25 lander over dry sandy soil. And you can do that very easily on most of the HF bands using 18-meter spider poles. You're right up there with the good performers. And in fact, significantly better than a VDA at a lander above the sea.
How would an elevated ground plane come on there if you haven't got it?
You're really doing it to me today, aren't you, John? The second half of this slide, of this table, has a 2 elevated radial ground plane fed at the 0.6 lander. Look, we're down at -1 dB relative here, which is 9 dBs worse than the worse than the best performer on the table.
That's a low angle, is it?
This is analysed on that path between London and ZL7 in this case. And the figures, sorry, this was the NUI table, not the ZL7 table. The angles and the numbers are very similar for any of the deep Pacific locations because it's low angle radiation you need all the time. So as I said, this is analysed on the London NUI path. So looking at that, if I just go back, the decision was made for NUI to use inverted V dipoles on tall spider poles. And they were oriented with maximum radiation in the north-south direction. If there was any long path propagation, and there was at times, then we'd be able to take advantage of that with those elevated ground planes. Did they work? Absolutely they worked. I need to refer to my numbers here because I can't quite remember everything. But if we look at... oh, it's on the next slide, actually. Oh, it's on there. 37% of QSOs were with North America, 31% with Europe, and 29% with Asia. So to get that percentage of European QSOs is pretty good. We've got Japan and North America, and that's where the lion's share of the QSOs are going to come from. So it's interesting, having made this decision, the 20-meter dipole on an 18-meter spider pole, it was 2.2 dBs down on a VDA on the ocean edge. It's 0.3 of a dB up on a VDA at 1.5 at the top of a cliff, and 4.3 dB up on a VDA over dry sandy soil. That's why we transferred from VDAs to inverted Vs. Now, ZL7, the third of the DXpeditions, introduces a new problem, which is remembering that Europe is a priority. From ZL7, Europe's in every direction. So what do you do with your antennas? Well, dipoles are directional, no beams and rotators. We need a directional antenna for that. The first thing that comes to mind is an elevated ground plane. But we saw from the previous slides, from the table, elevated ground planes are way down gain-wise compared with the alternatives. So what are you going to do? Well, as I said, simulation shows that the gain is way down. But that is using a transmit and a receive antenna that are broadside to each other, which is not going to be the case on the ZL path. It's going to, the azimuth varies, so you're going to get a whole distribution. So what happens if you begin to move away from broadside? What happens at 45 degrees to broadside? And what happens with the end fire? Because you're going to need radiation in those directions to meet the QSO goals. Well, again, so back to the old simulation technique. And if we look, one of the great things about VOACAP is you can rotate the antennas relative to each other, which is exactly what we did. This is the results we obtained from that. So, as you'd expect, that broadside V is up at the top of the chart there. It's the best performer. And then the blue line shows the ground plane with the reduced gain, which we don't want. But look what happens at 45 degrees with the V. Then, actually, the elevated ground plane is a better performer, an inverted V at 45 degrees. And at end fire, wow, it easily wins. So although the absolute gain is down on the elevated ground planes, it made sense to use them because we just didn't know which direction the signals would come from for Europe. We'd want to be working all azimuths. Now, one of the questions that always gets asked, of course, with elevated ground planes is, how many radials do you put down? And you'll see all sorts of interesting numbers, people saying 2s and 4s. It turns out that if you've got enough altitude on them, then 2 is sufficient. And this is the plot of the 20-meter elevated ground plane on the spider pole. The plot's at azimuth plot at 13 degrees of elevation. And there's a loss of 2 dBs of 0.2 dBs of gain in the weakest direction to the maximum direction. So 2 radials with height is sufficient. Drop the height down, and you do need to go to 4. Get on the ground, and you need lots and lots. So, conclusion, 2 radials was sufficient, and that's exactly what we did. Now, put this slide in because we had a really hard-nosed logistics manager who told us the antennas weighed too much and that we'd got too many bags. So we needed to get creative in terms of how to build these things. And this is actually a 10-meter and the 20-meter ground plane on the same pole, fed with the same feeder. We worked out that the chances of wanting to be on 10 meters and 20 meters at the same time was minimal. It wasn't sporadic E-season, so we were going to be okay. So we constructed that, and that was a great performer. And just to extend that, at home I've been using a 3-band version of that, which performs extremely well. And it's easy to make, and again, you can see quite a bit of Sainsbury's kitchen chopping boards in there used in the construction.
Is that open wire feeder?
No, it's not. These are the 2 radials, and that's the radiating element. These are just the supports. That's on the top of an 18-meter spider pole. Right, going back to John's question, did all this stuff pay dividends? And this is QSOs by continent from 7. And absolutely fantastic. 38% of the QSOs were with Europe. We met our goal. 29% with Asia and 24% with North America. You begin to think, well, is it because all Asians and all North Americans have already worked ZL7? Don't think it's that. I think we just managed to get a good signal. Well, we managed to get signal into Europe. We could have been stronger if we'd have chosen to just be to focus on one part of Europe, but we decided to be fair to Europe. Just a quick note on the LF antennas. The 160-meter antennas were always an 18-meter tall T antenna on a spider pole. So vertical section running up the side of a spider pole and then teeing off in 2 directions at the top. Worked extremely well on E6 and ZL7. I don't know why they didn't work well on TX6. Yes, it is, yeah. It's quite cool, actually, an 18-meter spider pole, because you can do the 2 T-bits, and you can drop them down and cut the end and trim them from the ground. The maths just works out perfect for that. On 80 meters, then we had 18.3 meters of wire. It had to be slightly helically wound around the pole to fit on an 18-meter spider pole. That resonates at the top end of the band, and we just put a piece of series inductance in to bring it down to the CW end of the band. Having said that, I don't think we had any SSB QSOs on 80 meters.
Why was the 160 antenna close to the sea as well?
In terms of wavelengths, yes. Physically, well, it was on NUI. It was probably a wavelength and a half from the sea. And I think it had at least 32 radios, probably more.
The T section, was that broadside to the sea?
It was on NUI, on ZL7 it wasn't, but again, if you look at the analysis of that, it's not a great difference between the broadside and the end-fed. I can't remember the numbers, but it's less than a dB.
Is it a single element 30 watts?
Yeah, yeah.
And how is it fed?
So I was using a transmission line transformer. I think its base impedance was about 18, 19 ohms. And I've got a little rig expert that you can put on, and then I built a transmission line transformer to feed it. Oh, lots and lots, and it's not much fun putting them down in the rain. Yeah. As long as we could get, yeah. 40 meter always used elevated ground planes. Some stories I could tell there, but I won't because we've not got time. And for 30 meters, inverted Vs and elevated fed ground planes. 6Gs haven't sorted out receive antennas yet. We take all the bits and pieces to build beverages. We never do a good job of it. On ZL7, we took Dave's shared apex loop antenna, which actually works quite well if there are no other transmitters on at the time. And we had 4 stations on. And if Nigel's banging away, TXF, if he's banging away on 30 meters, it's not a good idea to ask him to go QRT at sunrise and sunset so that you can work some low band DX. He goes all grumpy. And so we ended up using that antenna because of the interference from the blocking from the other stations. Thanks to the G members for participating in all of this, and Dave in particular helped a lot with the modeling and the antennas. But the team is Hillary, 4JKS, Don, 3BJ, Nigel, TXF, Chris, David, Don XT, Dustin, and myself. So, time for some questions if anyone wants a question. Yeah. Ah, right. Right, there's actually 8, and you sort of get, and each expedition's had 7 operators on it. But as I said, 6G was a crowd-named concept, and it comes from the TX6G, I believe. Yeah.
What about the hex beam? You mentioned a hex beam earlier on, but you didn't mention it through the analysis.
Okay, apologies for that. The hex beam performed quite well, and it wasn't particularly high. It did perform well, but it was susceptible to radiation because it's a multi-band antenna. It was susceptible to transmissions from the other stations, and it also radiated any mush, any broadband noise that was created on those transmissions as well. Sorry, on its own transmission. So we decided in the end not to use it. We used it for quite a bit on 12 meters, didn't we? It performed very well on 12 meters. Yeah.
I wouldn't recommend it for a multi-station expedition.
No.
For a one-man expedition, great antenna.
Yeah. More questions? Come on, John, you've been quiet for at least 3 minutes now.
So the VDA,
Yeah.
thinking of one-man expeditions, is there an easy way to make it multi-band?
Someone has done it, haven't they?
Have they?
I've seen a 2-band. Is it the French guy?
Yeah, Laurel,
Yeah.
BKB.
I think if you look on his website.
So he was the guy that modelled the original VP6DX.
Yes, he was, yeah.
He's kind of the godfather of the VDA.
There's no reason why it shouldn't work.
Well, the construction of it, I think, would have to have different angles involved because the angle is quite important in achieving the 50 ohm impedance.
Almost a spider beam on end.
I don't know enough about spider beams to comment on that.
Yeah, it's still
On T32 we actually used them, but we had both bits vertical. So we had just 2 vertical,
Yeah.
one behind the other, fed in a similar way. But that, of course, requires quite a lot more hardware. And as he said, he had a really, really difficult logistics guy.
Yeah.
And I'll talk about that in my presentation.
One more question.
About difficult
You
antennas.
mentioned the 2-element vertically polarized quad as being the best of a bunch.
I think it's the amount of hardware in building them. Yeah.
Can you have separation on the VDA at the ends between the driven and the...
Yes, there is. Yes, the diagram had those numbers on, but it's about a foot to 2 foot. Let's go metric, should we? 30 centimeters to 60 centimeters separation between the ends. That actually makes the construction quite easily because you run the wire up from the end of the booms to an insulator, and then you use an insulated cord to the actual top of the mast section.
Super critical, but it is a dimension you want to take care of. And again, F4BKB site talks a bit about that. So until F4BKB, until the salt gets on the insulator. Yes. which we had at TX6. And they sparkle quite nicely at night. Yeah. But you just clean them off. Rinse the insulators and rinse the cords because the cords get salted. The salt is every couple of days.
Is there any sensitivity to the height of a VDA above the watery ground plane that we've got there? I've never seen any references to that. It's important to get it over salt water if you can, but once you've got it there.
That was one of my slides, which was what happened when you increased it from 0.1 of a lambda to half a lambda.
A VDA?
A VDA, yeah. And you keep going higher, and as I said, you begin to get more and more fingers in the elevation radiation pattern, and you get more and more useless radiation.
So you want to get it as low as you can without getting it wet?
Yeah.
I'm just thinking, we go to Flatham Island for IOTA for many, many years. It's an interesting location. It's 100 feet above salt water, the Bristol Channel. But the island where we put the aerials is on an old disused, they've removed it, an airport beacon. So there's a massive copper ground mat which the airport authorities put down on the island because in the old days, aeroplanes honed in on direction.
Yeah.
So there's a massive copper mat underneath. So we put our vertical on the copper mat, round to it. And then, but the island where it is, it's only 50 meters wide. So it literally is sitting in the middle of the ocean. It's like Scarborough Reef. It's sitting right in the middle of the ocean. And it's a nice location. And I'm thinking, because it's 100 feet high, would we lose a lot with a VDA?
Yeah.
But the antenna which blew, because we've given up taking Yagis there now, what we put up, because when we went to American Samoa, the island of Oahu, Titan X built a new antenna. Nothing new about it. All it was a vertical dipole, insulated at the bottom and fed in the middle with open wire feeder. So we put the vertical dipole with open wire feeder on Flatham, and it outperforms anything we would have put there sitting on that ground mat.
So one of the rules for antennas in the sea is vertical antennas, you will get sea reflection gain from them. Horizontal antennas close to the sea, the sea makes very little difference. But any vertical antenna will work it to some extent.
What was it proved it because the doubt in Thomas's mind was saying you've got to have beams, and when just by having it in Samoa, I was blown away. I thought it works. It is right by the ocean. So you put a vertical, and I made it unique. Take a dipole with a wire vertical.
Yeah.
And feed the wire with open wire.
Your verticals are going to work. Yeah.
And it just blows you away.
Yeah. Chris, so is it time to end?
We got
Thanks for the comments, guys.
any last questions?
One last question.
Okay.
So I've always wondered, when the tide goes out, is there enough residual kind of salt, damp salt in the sand to have a positive effect?
Well, so we haven't measured that yet, but one of the things that the 6Gs are looking at for their next DXpedition is finding a location that we can make that very measurement with. That's a rather corny way of saying I haven't a clue.
When Superman would do your...
Okay. Right, time to wrap it up. Thanks very much, Mike.
Okay. Good.